Hello, my name is Oliver, and today I'm going to be talking a little bit about how quantum computing can improve the emotional quality of art. Now, what is the emotional quality of an art piece? Well, I believe that the emotional quality of an art piece is derived through the individual's rhythm. The rhythm of an artist is given kind of like by their internal clock. So, the way that I place my strokes on the paper and the rate at which I do it is my own personal rhythm. How has the emotional quality of art changed over time? Because artists didn't have nearly as many tools back then as they do now, their effort might have been more focused into producing accurate drawings rather than emotional drawings. Currently, we have different tools. We have tools that allow us to produce these scientifically accurate and proportional drawings with ease. So we can place our efforts in other areas, such as the emotion of the drawing. How can quantum computing help with the emotional quality of my art? Well, let's reimagine the problem. Rather than thinking directly about how quantum computing can help the emotional quality of my art, let's instead think about how I can maintain my emotion in a piece within the time frame of feeling that emotion. Then perhaps our technology can help solve our problem. In order to start to understand this project, let's dive a little bit deeper into the GAN algorithm, which is the heart of my program. The GAN algorithm stands for General Adversarial Network. Generative means that the algorithm is trying to generate new data. Adversarial means that we have two competitors in our adversarial game. One, we have a generator, and two, we have a discriminator. Finally, we have network. Network refers to neural network, which we'll be using to build our program. Okay, so now that we've broken down the problem and what algorithm we're going to be using to solve our problem, let's talk a little bit more in depth about what this algorithm is really doing. So here we have our diagram, and on our diagram, the first thing that we're going to do is input some random noise into our generator. So you can see on the left-hand side there, we have some long column vector with a bunch of random numbers, and they could be positive or negative. We're going to input those numbers into our generator, and then the generator is going to take that random noise input and it's going to generate an image. Now, we're going to take these generated images and we're going to feed them into the discriminator along with our real images. Once we feed these images into our discriminator, the discriminator is going to try its hardest to determine whether or not the image that it was fed was real or it was fake. Then, after it determines if the batch of images was real or if it was fake, it's going to return back our loss. So that way we can keep track of how our system is performing. Okay, so now that we have our generator and discriminator set up to play their adversarial game with each other, we can start to train our model. The first thing that we want to do to train our model is load our dataset. And one thing you'll notice about the dataset is that it's a little bit augmented, and we're going to want to do this on purpose. One reason is so that we can include the variance and the accuracy of our generator. If we give it images that are too accurate, it might overtrain on the same images. So this way, we want to provide a lot of variance so that we can make sure our generator is still learning over time. The second thing that we want to do is define our GAN based on the scenario. In my prescribed case, I want to move this black pixel, which is on the left side of my screen, and I want to move it over to the right. And so we're going to define our generator for a linear movement. Okay, the last thing that we're going to want to do is we're going to want to train the discriminator to distinguish between the real and the fake images. We also want to train the generator to fool the discriminator. Finally, we're going to update and train for multiple epochs. Now, let's learn how to build the generator. The generator is a parameterized quantum circuit, and it is an Ansatz circuit. And an Ansatz circuit is composed of a wide range of quantum gates that are typically rotations or angle rotations. And it's designed to be able to represent a wide range of quantum states. Now, the first thing that we're going to want to do is define our function to build the quantum generator we're going to set the number of qubits that we're going to be running through the generator, and then we're going to create a quantum circuit with that many number of qubits. Now, for each qubit, we're going to initialize with a Y gate. That's just the encoder qubit. Next, we're going to apply a Hadamard gate to all of the qubits, which is just to initialize all of our qubits into superposition. And then we're going to create our Ansatz circuit by using the efficient SU2 package in Qiskit. Okay, so next we're going to go ahead and build our discriminator. The first things first, we're going to define our function, then we're going to define the input shape, and then we're going to define a certain number of convolutional blocks. Now, since we're running a really simple circuit, we're only going to be using 3 convolutional blocks, 3 or 4 convolutional blocks. But in general, with the increasing complexity of your project, you're going to want to use more convolutional blocks. Now, in each convolutional block, we have a convolutional layer, which extracts the features from each image. Then we have the activation layer that introduces nonlinearity. And then we have the dropout layer that drops unnecessary or overfitted neurons within the neural network. Now, with each convolutional layer that we've added, we've actually increased the number of information as well as the number of parameters that are included in our images. So then finally, after we've introduced each of these convolutional blocks, we're going to go ahead and add a flattened layer that's going to collapse our image back to its original size. Now let's actually get into training the generator and the discriminator. Okay, so inside our training loop, we're going to want to go ahead and say that for each epoch, we're going to take some images from the generator and we're going to take some images from the data loader. Then we're going to first train our generator. We're going to generate our gradients, then we're going to compute our loss, then finally backpropagate and update our generator weight. We're going to repeat a similar process for our discriminator. We're going to first compute our gradients, compute the losses, backpropagate and update our weights of the discriminator, and then during this process we're going to update every 5 epochs the losses so that we can see how our generator and discriminator are performing. Now, in order to generate the intermediate states for my final animation of my project, I'm going to apply some unitary operator to the end of my Ansatz gate. This unitary operator is a time evolution operator that also contains the Hamiltonian. Now, the Hamiltonian of our system is going to encode the trajectory of our path of our pixels and also some other information about our system. Here's an example of what it looks like after we've applied our Hamiltonian. Because we're applying our Hamiltonian to generate our tween images, we actually save a lot of computation time as opposed to having to generate each tweened image. Think of this as a metaphor, as instead of an artist having to draw each individual frame for his or her animation, they might be able to just evolve in time the state of the animation, so that way they don't have to draw each individual frame. Now that we've broken down all the necessary components to build this program, let's go ahead and walk through the code. So the first thing that we're going to want to do is import all of our necessary packages and also define the important directories. We are going to be animating some 16 by 16 pixel images. We're going to use 16 qubits and we're going to have a batch size of 16. The next thing that we want to do is import our dataset. Now you can see here, this is our imported dataset. I've applied a little bit of some transformations to our images, and each of these are just the individual images of our dataset that I've printed out, just so we can see how they vary from image to image. Okay, so now let's get on to building our neural network. The first thing that we're going to build is our generator. The generator is built using a quantum component, as we discussed earlier, so the first thing that we're going to do is import our necessary Qiskit packages. In our actual function, we're going to define the number of qubits as 8. We're going to build our quantum circuit using that number of qubits, and then down here we're going to compose it using our Ansatz with the efficient SU2 as we discussed earlier. And here's our circuit. and it looks pretty much how we expected, except I've added a couple of extra layers to increase the accuracy of our generator. Okay, so let's go ahead and test out that our generator works. Here, I've just given it some noisy input parameters so we can see the generator generate some images. So the next part of this step is to go ahead and build our Hamiltonian. Now, I'm not going to get into the details, but I'll show you an example of what it looks like after we've applied our Hamiltonian. So I went ahead and applied our Hamiltonian operator to the generated images that we made earlier, and we got a little bit of difference. You can see that on the far left we have our initial state, and we evolved it 3 times and each time, it changed a little bit. It got a little bit lighter, which is cool. It doesn't really mean a lot right now, but we haven't really trained our parameters, so we're just seeing that everything works. The next thing that we want to do is go ahead and build our discriminator. Now, in the discriminator, I went ahead and defined 4 convolutional blocks to make sure that we're getting enough complexity to make sure that our discriminator is able to learn. Our input layer is going to be a 16 by 16 image, and it's going to have 1 dimension, and it's going to be in batches of 16, meaning the images are going to be grouped together as groups with groups of 16. So in the first convolutional layer, we're going to increase our dimension to 32. Then in our second convolutional block, it's going to go to 64 and double again to 128, and then again to 256. And then finally, we're going to flatten our layer and go back to our 1-dimensional, and that will be the output of our discriminator. Okay, so now let's go ahead and define our training loop. So the first thing we're going to go ahead and do is define our loss. And we're going to be using the BCE loss function from PyTorch. Okay, then we're going to define our optimizers, and we're going to give them a learning rate. So let's go ahead and run these. And then finally, we're going to define a little bit of a function just to see what our plot looks like as we're training our generator and discriminator. So now I'm going to go ahead and break down the training loop for our model. Now at the top, I've defined that I want to run this program for 20 epochs. And 20 epochs is usually just enough to see if your program will go through mode collapse or not. And we're going to get into our loop. So we're going to say for each epoch, we want to take some fake images and some real images, and then we're going to throw them into the discriminator. We're going to throw them into the discriminator right here, and then we're going to calculate our loss. We're going to append our loss and update our weights, and then we're going to do a very similar thing for the discriminator. Okay, so let's go ahead and try running the training loop. Okay, so the program took 6 minutes and 25 seconds to run, and you can see that the discriminator, the loss rate pretty quickly went to 0, and the generator loss spiked and went up and maybe started to stabilize at around 7. So this is what I would call mode collapse, and unfortunately I haven't found a solution to this yet, but we can go ahead and still see what our generated images might look like. So let's go ahead and test our generated images, and you can see here that it didn't really learn much, it just generated some noise. With this process, I actually was able to generate some successful animations of my 1 pixel. However, it's important to note that I was able to generate these animations by making the assumption that I had a white background and also using the assistance of some guide frames. I hope that in the future I'm able to fix the mode collapse that I was experiencing with my most recent program, and that I'm also able to implement different movement Hamiltonians for the system. Anyways, I hope you were able to learn a little bit about how quantum computing can improve the emotional quality of art and how these algorithms tend to function.